Hi, my name is Yu-Dai Tsai. Today I'm going to talk about new dark matter theory and experiments in particle physics renaissance. And I'm a postdoc at Fermilab. I received my PhD at Cornell in August 2018. So before I start my talk, I would like to remember Professor Dr. William DeBoer. About 10 years ago, I was at CERN as a summer student. And at that time, I was trying to start some theory study. And he really helped me a lot. And we had a lot of email exchange. And he actually even interviewed me for the Karlsruhe PhD program. So I really appreciated that. And this is to pay tribute to him. So particle physics renaissance. It's about new ideas testable in small-scale experiments and new experimental proposal. These are thriving at this moment. And the line between theories and experimentalists is blurry. And this is how things started in the beginning. But now it's kind of, people are coming back to design a lot of the small-scale experiments. There's a strong connection between subjects, including particle theory, astroparticle, and cosmology. And so this is what I do in this this kind of so I build new theory and new models from my senior collaborator, and this is the blackboard. So this is just to demonstrate that we're doing things still on the blackboard. But also I'm very interested in directly involved. Either I propose experiment myself or help design the experiment. So these are the things that I also do. And also look into like astrophysical stuff. So this is a Crab Nebula. So this is from a supernova remnant, and supposedly there should be a neutron star somewhere inside. And also I look into the cosmic ray shower, and maybe you can produce new particle by having that. Yeah. And the thing I do is I try to be creative and make connection between different subjects. So today I'll focus on new dark matter scenarios and new dark sector experiments. And SM means standard model of particle physics. DM means dark matter. Black text is for all audiences. Purple text may need extended discussions. And it can also be homework for students. And there are many transition slides, so slide number may go a little bit, but it's a lot of transition slides. So yeah. So the theme of my work I will talk about is I will connect dark matter to standard model, and I will consider observation, theory, and experiments, and finding the most promising testable dark matter. Here's the outline of the talk. First, I will talk about resonant self-interacting dark matter related to quantum chromodynamics and matter-antimatter asymmetry. For the Millicharged particle searches, I do the analysis and experimental proposal. I'll talk about analysis and experiments I propose. This is probing dark sector related to neutrino experiments and neutrino physics. Then I'll give an outlook. So there are kind of deep mystery that drives me into the physics study. What is dark matter, charge quantization, and also neutrino mass and neutrino interactions. There are many more, but these are the things I listed. They somewhat are related to this talk, like either closely related or a little bit related. Yeah. And these are Vera Rubin and Professor Vera Rubin and Professor Paul Dirac that they did a lot of related study about either charge quantization or the discovery of dark matter. So we understand this dark matter to a certain degree. We understand how much of them do we have. And this is like eating a cheesecake. We are only eating a small slice of it. And how do we really know about dark matter anyway at this moment? The answer is we know next to nothing about dark matter, but we have overwhelming observational evidence. Either it's astrophysical or cosmological. And today I will focus on the galactic rotation curve But CMB and bullet clusters are also significant reasons why we believe they are dark matter. So this is a rotation curve. So you can see that things on the left-hand side, the outskirt is moving much slower than the one on the right. And this is because there are invisible matter inside here on the right-hand side that is not present here. So things moving here are much faster. And here you can also look into a specific galaxy, Messier 33. You find out the velocity curve measured and expected from the lights are very different. So it means there must be missing matter here. And the homework for student is the Newtonian physics example. So if you have a point mass, then the VC will, the circular velocity will be this. And if you have constant density, it will be proportional to R. So in reality, things are kind of in between. And that's kind of telling you that not all the matter are concentrated here. There are things here, and you can use VC to relate to M or rho, which are the density. Okay. So, but let's look a little bit deeper. So there's something called small scale structure study. So this is the study of individual small galaxy like dwarf or spiral galaxy to larger objects like galaxy cluster. And this is as opposed to the large scale structure, which is galaxy of and form a filamentary structure, and the typical scales in hundreds of millions of light years. So it's much larger scale. And so once you have a magnifying glass into these galaxies, you find out there could be several problems. Of course, some problems in these systems are much better resolved by now or better understood by considering baryonic feedback. So when I say baryonic feedback, meaning that you have the baryon that is pushing like the gravitational wall and affecting the distribution of dark matter. Usually it's from like supernova processes. So that's something that is a proposal to explain a lot of these problems. And I will talk about one of these. This is called core versus cusp problem. So core, meaning that so you can look at the dwarf galaxy DDO 14154. DDO actually has nothing to do with physics. It's David Dunlap Observatory. Of course, David Dunlap is very important, so it is related to physics that way. But the DDO is not a physics term. So DDO 154. You have these velocity data, and then the red one can fit the data pretty well. But if you do the whole dark matter or collisionless dark matter simulation, you find out it's this profile. So there's a huge mismatch for this consideration. But of course, as I say, supernova might be able to help explain that, but it's kind of, it's a little bit more complicated. You have the knob to tune, things of that nature. So to some people, this is still up to debate. But to me, the real take I have about this is small scale structure may be the only place that we can find dark matter interaction beyond gravity in a galactic scale. In the best case scenario, it will help us find and understand dark matter. In the worst case scenario, it will provide strong constraints on dark matter interaction, self-interaction, which is still very interesting. So the theory program is self-interacting dark matter. So I will talk about small scale structure opportunity and the resonant self-interacting dark matter, which is my work. So the dark matter self-interaction is proposed by Spielberg and Steinhardt. Dark matter collisions thermalize the dark matter particle in inner halo and smoothen or core the distribution. So it's called core. And halo profile are those related to the velocity average, a scattering cross-section per unit dark matter mass. So notice that there's a V inside here. So it's sigma V thermal average. So this V is important. In dwarf, is 20 kilometers per second, and cluster is 2000 kilometers per second. And then you can do a semi-analytical study about this, and it's very interesting. So what you find out is that, this is in this paper, done by this paper, that you find out that there is a preferred velocity-dependent cross-section for different scale. The way they do that is they calculate the rate times the time. So you have a rate, which is depending on the sigma v over n times rho, times the time, which is the age of the universe. If it scatters once, then you say it's thermalized, you have the isothermal distribution. If it's scattered less than one time, you say it's basically collisionless. Then you have NFW. And then you feed this back into the observation. So that's how you determine this cross-section. And you would tell me, oh, this can be flat, right? Well, yeah, it can be flat, but the flat one is actually velocity dependent. So the flat one is sigma proportional to 1 over v. So dark matter self-interaction from this perspective prefers velocity dependence. Of course, in reality, the error bar will be even larger because you have to consider baryonic feedback. But my take on this, the minimal thing you can take from this is at least your cross-section cannot be much larger than this. So there is kind of like velocity-dependent constraint on self-interaction. So you cannot have this cross-section here, and this is velocity-dependent. So that would be the interesting thing. And furthermore, there is this very nice model, toy model. They can fit the observation with a light mediator. But this is a little bit ad hoc. Why do we add a light mediator? I mean, it's up to debate how we think about this. But then there could be also a quite attractive way to do that, that is directly through QCD and strong interaction. So it's dark matter self-interaction and dark matter Standard Model hadron interaction. As you can see, the cross-section is not so far away from each other. So maybe you can build this self-interaction from hadron interaction. So that brings us to the strong resonant self-interacting dark meson. It's a solution to small-scale structure problem and have interesting experimental signatures and can be tested in near future. So the idea is very simple. You have the dark matter going through something that has a resonance. Resonance meaning the mass is about 2 times of the dark matter mass. And we'll assume delta to be positive for this talk. And the velocity dependence going like this can be achieved with the intermediate particle R. They help provide a self-interaction cross-section to be a sum of a constant piece, constant like this, the constant, and the Bragg-Wigner resonance go like this, a peak like this. So resonance in a specific velocity. A little bit more detail, it's a constant plus this Bragg-Wigner resonance, meaning that when EV is equal to this mass difference, you can have a peak. So that will be interesting. And so immediately you think about this, so that's great, but what kind of model does it come from? So it could come from something very similar to dark standard model, that you could have a resonance. You could have something similar to B0, B0 bar, going to Upsilon 4S, come back to B0, B0 bar. And okay, that's interesting. And not only that, you also have K-on and phi that can also give you that. So inspired by these, we want to build a model. But before we build a model, let's look into standard model. So even the standard model have all these very interesting resonance and can be kind of understood, right? So these curve, these dots are all standard model data points. So nothing is dark matter here. So then you can connect these dots and say that, okay, my pseudo scalar mass grows like this. So that's very interesting. And furthermore, each of the vector meson have this kind of level. So you can see here, when this black curve goes to next to the green, that's when a resonance happens. So resonance will happen here, here, and here. And it's almost not a coincidence. So it's very intriguing, and we want to use that fact. So that brings me to asymmetric resonant dark meson. It's an asymmetric dark matter model connecting dark matter mystery to the standard model mystery. So resonant dark meson, you can link dark matter to standard model. So you have the dark matter going to resonant, go back to dark matter is very similar to B0 bar, go into Upsilon 4S, come back to B0 bar. And B is a B bar state, which have a heavy quark B and one light quark D. And MB is much larger than lambda QCD, so it's a QCD parameter. And option 4s is the fourth excited quarkonium state. Okay, so this is the state as the example we want to model based on. And that's why we find out this very nice paper by Chris and John that is very, very informative for us because and they did it long time ago. So we learned a lot from them. And then we just directly use the same consideration that we can build this model. And I'll get into a model a little bit more. But the name of the game is go to the higher level, because with the higher level, you can hit the resonance easier. So we define something called close to resonanceness, which is how close you are to hit the resonance. And this is delta n divided by mq is proportional n to the minus 3. So the higher the level you go, the easier you can hit the resonance. So this is very interesting. So we want to build these things here. So then now we have all the ingredients. We have one light dark quark, mu prime, two heavy dark quark, C prime and B prime. Then you can form these heavy meson states, B prime and D prime, and we allow them to, we actually make them to be asymmetry. You have a D prime, B prime, go to D prime, go to option NS, come back to B prime and D prime. So this is cool. And it will go through an NS state, and the N will decide it based on your MQ over lambda. It will be the closest N. Okay. So that's the, and the B prime and D prime are set by their asymmetry, which I'll explain. And they're also protected by B prime, C prime quantum number. And the asymmetry is as follows. There's this asymmetric dark matter model. That the dark matter asymmetry is the same as standard model asymmetry with the same origin. So in standard model, you can see that I have this stuff here, and I'm existing. We have the internet. So it means there's more particle than anti-particle. And same origin can be said maybe for dark matter. And then you can create the same, a similar amount of number density of dark matter, similar to standard model. And then you will find out that the dark matter has to be 5 GeV, 5 times the proton mass, because the mass density have to be 5 times. So that's 5 GeV. So now we have our very attractive model. We have the 5 GeV dark matter, and we allow our MQ over lambda to be about 20. So you can go on the option 10s states. And then we actually find out very nicely the GBD option is actually very similar to the standard model value. So this is a success. And lattice QCD can improve our study. And you can ask me what happens to the dark pion. So we actually allow the dark pion to decay to dark photon, because the dark pion, we don't want it to be dark matter. And the dark photon is something I will explain a little bit later. It's kind of similar to standard model photon, except it has a mass. So you can decay through an actual photon to E plus E minus or lepton pair. Dark matter is 5 GeV, and lambda is about the same as m pi prime, and this has to be larger than 2 times of the dark photon. So this is again analogous to QCD, and so lower the mass of the dark photon is, the more likely we can hit the resonance, because MQ will push down the lambda, and lambda will push down the dark photon mass. So if you can push down your dark photon mass as low as possible, that would make you easier to hit the resonance. And this is the dark photon model. Then you have kinetic mixing to couple your photon to your dark photon. Okay, and a side note is that I actually proposed that experiment. So not fully proposed, because previously there's an idea of removing the wall and put a detector here to search for dark sector particle. But I feel like that is a very nice idea, and you can do a lot of things with that, but it could interfere the experimental operation. And you could also it's much more costly. So a more natural way is just do things behind. So this is my proposal. I propose to do things behind an iron block to put a detector here to search for a decay particle. And there's a lot of things one can do here, including dark photon search. So finally, this is a dark photon part of the story. Again, dark matter mass is fixed, and we want to push down a lambda. So, and the lambda then will push down dark photon mass. So dark photon mass around 100 MeV would be preferred. And the kinetic mixing range is pretty large. And we're thinking about maybe there's a way to narrow down this, but not yet confirmed. But yeah, this would be the interesting regime. And there happens to be a lot of search in this regime. Okay. So recap of why is this exciting is a general scenario to naturally give the resonance structure, has interesting structure similar to standard model QCD, can easily connect to lattice dark QCD, has signature that can be searched in experiment and testable also in astrophysical studies. And in these, you can analogous to the 5KK system, which is a light quark asymmetric dark matter model. Or you can connect that to our previous work. This simply is not proposed by me. It's proposed by other people. I actually have the reference in the later slides. But there's also the elder paper that is proposed by me. Not also by actually should be say proposed by Eric, which when I was a PhD, I worked with the postdocs Eric, Maxime, me, and Nick, and their references listed in the back. So I should add it here and see our paper for more detail. Okay. So there's also ongoing astrophysical studies. That is very interesting. So actually, so we are trying to look into this regime to see if we can better differentiate different models. And recently, there is actually an interesting paper that suggests that maybe resonant self-interaction is more preferred because they find out that in the lower velocity, it seems that you need a very small cross-section. But my collaborators disagree with some of the results, so we're still trying to figure out what is the actual situation right now. So there are some assumptions that we're still debating. So this is something that is ongoing. So let me jump to the experimental program, searching for Millicharged and dark sector particle. I touched upon this a little bit about dark photon, but there's a lot more you can do. And this is my new experimental proposal analysis of existing and future data. So Millicharged particle is one of the simplest extension to standard model sector. It's a particle with small electric charge. And standard model U1 hypercharge is fixed by anomaly cancellation. We all know that. But additional Millicharged particle are possible. Why don't we see them? It's a mystery. And Millicharged particle is related to massless dark photon theories and charge quantization. And it's independently interesting without assuming it to be dark matter. It can be connected to superstring theory, string amplification, etc., etc. I also give out the reference in the end. And you can find Millicharged particle as least as interesting as finding the fractional quantum Hall effect. And Millicharged particle can also help explain the edges anomaly. Also, to save time, I put all these in the backup slides. And the model is extremely simple. This model, you can just write it down with a small hypercharge, completely legal. You will not get sent into jail, even if you're in Germany. This is totally fine. And naively, you will say, oh, it's violating empirical charge quantization, but it's fine. And we are simply searching for this Millicharged particle because to me, minimal assumption means the most robust constraints and probe. So Millicharged particle will have a charge is small. There's also Z coupling, but suppressing low energy. But this can also link to the massless dark photon theory, that you have a dark photon, a heavy fermion loop going to our photon, and in the massless spaces, this chi will become Millicharged particle. So this is also very interesting. And the search method is very simple. From my perspective, you can propose, not my perspective. The thing that I consider is proton colliding with the target or other proton. And then you can produce meson, and meson can decay to photon, and offshore photon go into Kai bar. And you can study the hard scattering. This is, for example, in the mini boon detector, or like proposed by Millikan, an original paper is by Haas, Hill, Izaguirre, and Yavin. That is scintillation. So you can use this scintillator to search for Millicharged particles. And I want to apply for all of them. Also, there could be a machine learning project for the ultra fine tracks for Millicharged particle. And this is a future project with student people and also with whoever students or posts are interested. Sorry. And then there is this Fermini paper. Sorry, first you can do things in the Dune or other neutrino experiment, and we proposed that, and we did some analysis and set some bound. And you can also do things in dedicated detector. So you put your Millikan detector downstream of a proton fixed target. You can search for things, and these are the production, roughly. Yeah, this is at Dune, but the production in the NUMI beam is about the same. Thirdly, an interesting site would be in the LHC forward regime. So you put your Millikan type of detector in the forward regime. And sorry, this is being reshaped previously. So let me drag it back to the original. Okay, yep. So this is the situation. You can put something in the forward regime and search for Millicharged particle. And you can place a Millikan type detector in the forward regime, and it can actually give you very nice sensitivity. And finally, you can study cosmic shower, produce dark particle flying to a large neutrino observatory, and you can also have some sensitivity. So finally, we have the compilation. We have neutrino experiments, which is the blue one. We have the Super K. We have the Fermini and Formosa. And this is kind of like I'm having 4 different kind of study for these. And Formosa may also be able to study tau neutrino magnetic dipole or dipole polar dark matter. And we just started working on this. By the way, the Dune curve is the updated curve by Ronnie, Jean, and Ornella. But I'm also initiating a new study with Dune, as I say, that is very interesting. You trying to apply machine learning techniques. And also I want to mention the idea of forward Dune. I am interested in moving the proto Dune detector downstream of LHC. And this room that people look into is called, as a proposal for physics facility, might be too small. So it's interesting to move this proto Dune in the forward direction to search for neutrino. And this is a paper from the Phaser-New. I'm not in the Phaser-New collaboration, but I'm very interested in collaborating with them in the future. But I was in the FPF, this FPF letter of intent, so I'm participating in this. So we're together with Felix and Jonathan and experimentalists and student. We're trying to see if this is a possibility. But down the road, I think it would be extremely exciting to spread the neutrino detector around and have these kind of forward neutrino detectors and build kind of like the forward neutrino campus, because you can have many of them spreading around to search for high energy neutrino. And as pointed out by the Phaser-New, there is a gap between the previous study and IceCube, so you can fill up the gap. Okay, so my research program is developing new and testable models, design new experiments, and my experimental proposal are long quest, and Fermini and Formosa, I'll talk more in 10 minutes discussion, develop new cosmology and astrophysical studies. And in the future, it will be very exciting to join KIT, and there's a lot of great collaboration opportunities. Let's find dark matter. Thank you. Cool. Finally done with this recording. Yeah.